Hello and welcome to our next section in Chapter 8, 8.8, Numerical Integration. Situations arise in which the analytical methods we have developed so far cannot be used to evaluate a definite integral. For example, an integrand may not have an obvious antiderivative, such as cosine of x squared and 1 over the natural log of x. Or perhaps the value of the integrand is only known at a finite set of points, which makes finding an antiderivative impossible. When analytical methods fail, we often turn to numerical methods, which are typically done on a calculator or computer. These methods do not produce exact values of definite integrals, but they provide approximations that are generally quite accurate. Many calculators, software packages, and computer algebra systems have built-in numerical integration methods. In this section, we explore some of these methods. Absolute and relative error. Because numerical methods do not typically produce exact results, we should be concerned about the accuracy of approximations, which leads to the ideas of absolute and relative error. Suppose C is a computed numerical solution to a problem having an exact solution x. So C is the approximation of the actual value, the exact value x. There are two common measures of the error in C as an approximation to x. The absolute error is just the difference between them, the absolute value of the difference between them. And the relative error is the absolute value of the difference between them divided by the exact value x. This is what the relative error is really important, and this is what we miss in a lot of news media, etc. And we'll look at that in just a second with our next example. The ancient Greeks used 22 over 7 to approximate the value of pi. Determine the absolute and relative error in this approximation to pi. I've left the formulas on the screen at the bottom left. This is a very simple problem, so go ahead and hit pause and then try this problem. So the absolute error is just the absolute value of c minus x, and c in the approximation is 22 over 7. The exact value is pi, so we put that in, c minus x, and simply do the calculation, and we get approximately 0.00126. It's approximate because this continues on. The only thing we're going to do different in relative error is divide this value by the value of the exact value of pi. And here we get c minus x over x, or in this problem, 22/7 minus pi over pi. I didn't put the absolute value of pi here because pi is positive. When we do the calculation, we get a relative error of 0.000402. It's a good idea to put relative errors in percentages because this is kind of a common language and a common understanding that we all have. And so remember, to do that, we move the decimal place over 2 to the right. And so we get 0.04%. Again, this is not 4%. This is 0.04%. When you have the percent sign, it's saying the actual number is moved 2 places back to the left. Okay, this is, to me, is where we get a lot of what I think is actually fake news because the news tends to report numbers in a shocking way. For example, they might report on the stock market drop and say, oh my God, the stock market had a colossal fall of 500 points. If they did the relative drop, it might only be 1 or 2%, which, you know, is not as exciting. It's not as scary as a colossal drop. And to me, this is the bigger problem with fake news, is we get some kind of actual numbers without any kind of context, which is what percents give us, is it's relative to the problem at hand. Okay, I did a little soapbox there, and let's move on. As we learned in Calculus 1, Many numerical integration methods are based on the ideas that underlie Riemann sums. These methods approximate the net areas of regions bounded by curves. Here we're looking at the midpoint rule. In Calculus 1, we talked about this briefly, but we use left end values or right end values for Riemann sums typically in most of our examples. And here we're just doing the exact same thing, but instead of using the left end value for a rectangle or the right end value for the first rectangle, we're using the midpoint, which is the halfway point between the two x values for each rectangle. A typical problem is shown where we see a function f defined on an interval AB, and that's this diagram here to the right. The goal is to approximate the value of the integral from a to b of f of x dx. Just as with Riemann sums, the midpoint rule approximations generally improve as n increases. And so if you remember from Calculus 1, what we did is we put a limit as n goes to infinity to find the exact solution of the integral of f of x, because that was the area under the curve. And again, midpoints are generally the best approximation of Riemann sums. You may again remember from Calculus 1 where if we did left, depending upon whether a curve was concave or convex, left end or right end curves would be an over or under estimate. And so in general, midpoints provide a better overall estimate of the area or the integral value. So let's try example number 2. Approximate the integral from 2 to 4 of x squared dx using the midpoint rule with n equals 4. Go ahead and hit pause. This is again review from Calculus 1. This is very simple about using Riemann sums, and see if you can remember how to do this. Since n equals 4, we're going to have 4 triangles starting from x equals 2 to x equals 4. So again, hit pause, try this on your own, and see if you can approximate the integral value. The first thing we want to do is to find the width of each triangle. Remember, the width of each triangle is b minus a over n, or the interval over the number of rectangles. So we get 4 minus 2, b minus a over n, which is 4, and we get the width of each rectangle is 1/2. Well, the next thing we want to do, since we're using midpoint rules, we have to find the value in between, in the middle of each rectangle. So we first have to find all the x values for the sides of the rectangles, or the grid points. And so we start at x equals 2, and then we add 1/2, and so we get 2.5, then we get 3, then we get 3.5, and then we get 4. And we can see that we have 5 points that are going to be the 5 sides of the rectangles, because we're going to share sides. Okay? Now that we have the sides of the rectangle, we can calculate the midpoint for each rectangle. So remember, each rectangle, like the first rectangle, is going to go from 2 to 2.5. So its midpoint would be halfway between there, or 2.25. The second rectangle would be between 2.5 and 3. So halfway between 2.5 and 3 is 2.75, and then 3.25 and 3.75. So what you're doing is you're taking x2 minus x1, which gives you 0.5, divided by 2, which gives you 0.25, and of course it's between them, then you're going to add that back to the first x1 value. So this will give you halfway between them, and then you have to add it to the x1. Okay? And I'm using each of these as x2, x1, instead of using x sub k minus x sub k minus 1, etc. So here's a diagram where we can see what we're talking about. Here's our function f of x equals x squared, midpoint rule, n equals 4 from 2 to 4. We can see all the x values, 2, 2.5, 3, 3.5, 4. Those are the sides of the rectangles, and then we can see all of our midpoints in there. Now we're ready to calculate the area, or approximate the area under the curve by summing up each of the rectangle's areas, which is of course width times, in this case, height. So the width is always the same, which is 0.5 or 1/2, and the height is going to be the midpoint value plugged into the function x squared. So what we have now is 2.25 squared times 1/2 plus 2.75 squared plus 1/2 plus 3.25 squared plus 1/2. Again, what we're doing is we're trying to find the height of this, so we plug in 2.25, the x value, into the formula x squared to get the height of that first triangle, and do this with each subsequent triangles. Since all of these triangles have the same width, we can sum all the heights first and then just multiply them using distribution, because this is 2.25 squared times 1/2 plus this times 1/2 plus this. So we can pull the 1/2 out and we get an approximation of 18.625. If we want to see how close this is, we can use the absolute and relative error formulas. The actual area of the region is 56/3. This is a simple integral to solve. We could have found that. And so here we have the absolute error of the approximation that we just did minus the actual value for absolute area gives us 0.0417. If we then divide that by the actual area, we get 0.00223. Again, expressing this in percentage gives us a 0.223%, which is about 1/4 of a percent. Okay, it seems relatively small, but it's conditional on whatever you're doing. Error, we often use these error rates for constraints or requirements. For example, how strong something might need to be if you're building something, and so that error rate has to be within a certain percentage. A relative error rate has to be within a certain percentage. This seems relatively low, but again, it depends upon the application you're using. If we're talking about bacteria, this may be a high percentage, and we may not be able to use the approximation. Let's look at another rule, the trapezoid rule. Another numerical method for estimating the integral from a to b of f of x dx is the trapezoid rule, which uses the same partition of the interval ab described for the midpoint rule. Instead of approximating the region under the curve by rectangles, the trapezoid rule uses trapezoids. The bases of the trapezoids have the length delta x, which is the same as what we saw in the midpoint rule, right? And we'd find the width of each of these by doing delta x equals b minus a over n, just like we did before. The sides of the trapezoid, of the kth trapezoid, have lengths fk minus 1 and f sub k, f of x sub k. Okay? So for this first trapezoid, the lengths would be f of x sub 0 and f of x sub 1. The formula for the area of each trapezoid is given by the graph, this up here, the area of the kth trapezoid. And notice what this is the height of the left side plus the height of the right side divided by 2 times the length of the base. So the left side plus the right side divided by 2, half of that, times the base. I think I might have just said divided by. Okay? So you'll notice that this bottom formula, which gives the trapezoid rule, which gives us the area under the curve, it expresses it as 1/2 of x sub 0 plus x sub 1, x sub 2, all the way through until you get to the last one, x sub n minus 1, and then plus 1/2 of the last side. Now, why is that? Well, remember, we're using half of sides, right? We're summing the sides and then taking a half, which really means half of this side and half of this side, because we could separate them, okay? Well, for the first rectangle, we use we use x sub 0 and x sub 1. For the second rectangle, we're using x sub 1 again. So if you put these in terms of 1/2, we'd have a half of x sub 1 for the first rectangle, plus another half of x sub 1 for the second rectangle. And so that's why the middle heights do not have the half on them. Only the far left side and the far right side have the half on them, or divided by 2, because we're using the rest of the sides for 2 separate trapezoids. Okay? And of course, just as with Riemann sums, the approximations generally improve as n increases. So let's look at an application of the trapezoid rule. We're going to do the exact same problem that we did in example 2, but instead of using the midpoint rule, we're going to use the trapezoid rule. I've left the formula here. Again, it's pretty straightforward. I'd like you to try this on your own by hitting pause and seeing if you can get through and get the actual approximate answer using this new rule. This is a little bit different than what we did in Calculus 1, so it's good practice for you to do it. I have left the formula right here. This is the area of a trapezoid approximation. Okay? So try it on your own. Just like before, the first thing we're going to do is find the width of each trapezoid. In this case, the base of each trapezoid is going to be the same as the base of each triangle, delta x, which is b minus a over n. That's going to be a standard. Next, we need to find the grid points. These are exactly the same as well. These are the sides of the trapezoid, which will mirror the sides of the rectangles that we saw in the midpoint. So we start at 2, we add a half, we get 2.5, and we add a half, we get 3. We add another half, we get 3.5, and finally our last half gives us 4. This gives us an image, as we can see here, of the trapezoid approximation, which should be a little bit closer since we don't have a lot of overlap or underlap that you can see here. Okay? So now we can go directly to the trapezoid formula. 1/2 f of x sub 0. Well, f of x sub 0 is 2. So we get 1/2 times 2 squared, because we plug that into the formula. If x is 2, then f of x is x squared, or 2 squared. And then the 3 points in the middle, 2.5, 3, and 3.5, we don't have halves on those. We just have those full values because we're using them in 2 trapezoids. For example, 2.5 is used in the first trapezoid and in the second. So 1/2 of x sub 1 for the first trapezoid plus 1/2 of f of x sub 1 for the second trapezoid gives us just that whole x sub 1. Okay? And then, of course, 0.5 times the, 1/2 times the last x value, which is 4, f of x squared, 4 squared, and then, of course, times the delta x, which is 1/2. If we do the math here, we'll get 18.75. And if you remember from before, our actual error was 0.0417. In this case, we have an absolute error of 0.0833, which is interesting because that's actually a larger error. Before we had 0.04, now we have 0.08. While it looks like it's a better approximation, evidently it's not. Okay? So let's look at example number 4, where we're calculating errors in the midpoint and trapezoid rule. This seems like a lot of work, but if we use our calculator, and this is really good practice, it's not quite as bad. Now let's look at the problem. Given that the integral from 0 to 1, x e to the negative x dx equals 1 minus 2e to the negative 1. So this is the actual value that it equals. This is a constant value, 1 minus 2e to the negative 1. Given that we know the actual value, find the absolute errors in midpoint and trapezoid rules with n equals 4, 8, 16, 32, 64, and 128. Again, what you're going to be doing is comparing your approximations from midpoint and trapezoid rules with this actual value 1 minus 2e to the negative 1. And you can plug that in your calculator and see the constant value that represents. Okay? I'm just going to show you one working through and explain how to do it with your calculator using n equals 16, which is the one in yellow there. Okay? So the first thing we have to do is find the width, and in this case, and the sides of each rectangle or trapezoid. We do that the same way we've been doing it all along. Delta x equals b minus a over n. So we get 1 minus 0 over n, and our n is 16 this time. So we get 1 minus 0, which is 1 over 16. That means each of our x values, our sides, equals k over 16 when we start with k equals 0, 1, 2, etc., all the way up to 16 in this problem. This is going to work for all problems. So for example, if we use n equals 4, we'd have 1/4, and x to the k would equal k over 4 for k equals 0, 1, 2, 3, 4, etc. Okay? So what we have here is the printout from your textbook, and so they've used sigma notation and a calculator to figure this out. Okay, so here is our k sub 1, k minus 1. Here's our x of k value. Here's our x of k minus 1 value, and so we get the function of this k value or x value times the delta x, which is 116, and we're going all the way from k equals 1 all the way to 16. Okay, this simplifies into this formula here, and you might remember this from Riemann sums, how we used to simplify. This simplifies to f of 2k minus 1 over 32 times 116. So this whole formula here simplifies to this. Now your TI-84 does have a summation key, or a summation app, and it's under the math button, which is, I think, the fourth from the top on the left. But be careful here. Notice this is f of x function. Well, what is our f of x function? And here we actually have a f of 2k minus 1 over 32. Well, our f of x is x times e to the negative x. But here we're replacing x with 2k minus 1 over 32, so you're going to have to plug that into your calculator. And so it's going to look like this for the summation. You'd have k equals 1, sigma from k equals 1 to 16, and then you'd have this here, 2x minus 1 over 32, e to the, again, it's to the negative x, so negative 2x minus 1 over 32 times this n multiplier of 1/16. Now you're probably going to have to put all of this in parentheses again. Play with it, but this will work. I tried it on my calculator, and it's good for you to do this so you can practice. Now here we have a much simpler formula for the trapezoid method that you can play with as well. And here you just have x over 16, e to the negative x over 16. Okay? Plus you'd have to figure out the two endpoints. Anyway, all right. So here they've calculated the error just by plugging this into their calculator. For the midpoint rule, you get 0.000163. You know, this value minus the 1 minus 2e to the negative 1. And then, of course, this value for the trapezoid. And there you get 0.00325. So I'm going to give you all of the errors for n equals 4, 8, 16, etc., so that you can practice these as well. But I think you should do at least a couple of these with your calculator to make sure you get the correct answer. This is a good one to try on both the midpoint and the trapezoid rule, hitting pause now, and then you can come back and try to do one all the way on your own. And then here's all of the errors. Here's the actual values you should get if n equals 4 for the midpoint method, for the trapezoid method, and then the error in the midpoint method and the error in the trapezoid method. So this is a good, you know, I wouldn't spend a lot of time on this, maybe do one or two of them, and but just make sure that you can use your calculator to do the summation for this problem. And then there's a couple related exercises if you want more practice. There's two more examples in this section that I want you to review on your own. These are examples 5 and 6. I'd like you to go into the text and actually review these examples. You have the e-text inside of My Lab Math or inside of eCampus. Example 5 is looking at world oil production and uses both the midpoint and trapezoid method to approximate the total oil produced between 1995 and 2011. And then example 6 I really want you to do, especially A, because it's really a context problem about using an integral to find the net change in sea level, again over a number of years. All right, I'm not going to walk through these. I think they're pretty well described in the book, and so I'm going to let you go ahead and spend some time and look through those a little bit more slowly. Now let's look at the Simpson's rule. An improvement over the midpoint rule and the trapezoid rule results when the graph of f is approximated with curves rather than line segments. Returning to the partition of the interval AB used by both the midpoint and trapezoid rules, suppose we work with 3 neighboring points on the curve y equals f of x. We're just going to work with this first shape, if you will, between x sub 0 and x sub 2. These 3 points determine a parabola, and it is easy to find the net area bounded by a parabola on the interval x sub 0 to x sub 2. So really we're looking for the integral over this between x sub 0 and x sub 2 if we create this natural parabola shape. Okay? When this idea is applied to every group of 3 consecutive points along the interval of integration, the result is Simpson's rule. So we're going to do the same thing here where we're going to create another parabola between x sub 2 and x sub 4. We're going to do the same thing here between x sub 4 and now we're into x sub k minus 1 and the next shape and the next shape and the next shape. Okay? When we do that, we get Simpson's rule, which is the integral from a to b of f of x dx equals, I put it here in larger, f of x sub 0 plus 4 times f of x sub 1 plus 2 times f of x sub 2 plus 4 f of x sub 3. And then it keeps going back and forth between 2 and 4 until you get to the very last value. So again, here what you're doing is the very first x sub value has no multiplier or multiplier of 1, as does the last multiplier or the x value, f of x sub n, it has a multiplier of 1. And then they alternate starting with 4 and 2 and 4 and 2, mainly because the coefficient on this parabola, the b coefficient, ax squared plus bx plus c, has a coefficient of 4 on it. Okay. The reason that we then have a 2 on it alternates with 2 is because, again, similar to the trapezoid method, x2 is not only used in the calculation of the area of the first area, but it's also again used in the calculation of the second area. So 1 for the first area and 1 for the second. And that's why it alternates back and forth, whereas x sub 0 and x sub n are only used for one area each. Now, I highly recommend that you go to the text to see the derivation of this formula. It's a very, it's a little bit complicated, but it uses the quadratic formula, and they do a good step down, but I don't want to take up 15 minutes explaining it to you when you can read through it, and I would guess 5 or 10 minutes and get the gist of it. But here is Simpson's rule. Our approximation is, again, f of x sub 0, and then 4 and 2 alternating coefficients of the next x points, x sub 1, x sub 2, etc. Noting that we have to create 3 points. So what we're doing is we have the interval, and it's like a midpoint here in each of those intervals like we've done before. And then all of that, and this is explained in the derivation too, times delta x over 3. So the summation of all of those functional values with different coefficients alternating 4 and 2 times delta x over 3. And of course, delta x is always the same, b minus a over n. And again, the delta x is the width of each of these shapes, if you will. I guess they're parabola shapes now, areas under parabolas. So let's look at example 7, how to apply Simpson's rule. Approximate the integral from pi over 2 to 5 pi over 2 of sine x over x dx using Simpson's rule with n equals 4. We're going to start this much like we've started every other problem by figuring out the width of each parabola section. Okay, and so that's our delta x. Our delta x is still b minus a over n, so we get 5 pi minus pi over 2 minus pi over 2 gives us 4 pi over 2, or simply pi over 2. From there, we want to look at and figure out each of our grid points. Starting at our a value of pi over 2, we then add pi over 2 to get pi, add pi over 2 again to get 3 pi over 2, plus pi over 2 gives us 2 pi, plus 1 more pi over 2 gives us 5 pi over 2, and so we've split the entire interval into 4 sections by having 4x values. You can see here now that we've got 2 sections of 3, so we're going to have 2 parabolas approximations, because we need 3 points for each parabola approximation. So our last thing to do is to use Simpson's approximation. And remember, since we have the first point, and then it'll be 4 times f of x sub 1, 2 times f of x sub 2, 4, f of x sub 3, and then back to just f of x 4, which you can see here. And then of course this is all over with delta x over 3. So remember, we need to plug in those values. So we get f of x sub 0. X sub 0 is pi over 2, so we get sine of pi over 2 over pi over 2. Then 4 times f of x sub 1, so 4 times the sine of pi over pi, and then 2 times f of x sub 3, and 4 times f of x sub 4, and plus f of x, the very last value. Okay. We can see then they've gone through at pi or 2 pi, sine is 0, so we've lost a couple of those values, and the whole calculation is here. All right. So again, this formula, remembering your points, they're in groups of 3, and it goes 1, 4, 1. But because we're doing it over the whole integral, in this case, f of x2 is actually used twice. It's used in the first parabola and the second one, and that's why there's a 2 there, because it counted for both of those. The last section is a very short section, and I do want you to review this in the text. It's like a half a page long, and really what it's doing is it's doing some calculations and some analysis to show you that each of the methods that we're doing in numerical integration pretty much has a similar pattern of error, a relative error, if you will, based upon the method that you use. And so they go through those calculations. So it's something interesting to look at, and you could compare some of them if you like. But I'm not going to walk through that. It's a very short section, but I would like you to review it.